Right, so let's discuss one more case study. This is a case study from the Cbse website, and you can see this is 55 oblique 1 oblique 1. I got this from the Cbse website, and the case study is based on the topic of Young double slit experiment. Very important topic for board examination and entrance examination. We will discuss this question today. The case study has 1, 2, 3, 4, 5 questions. Before I start solving this case study, I have a request that from my teaching experience, what I find is a lot of students forget the formulas of Young double slit experiment. So I have prepared a YouTube video on my playlist of wave optics. Please go and see that. The title is Young double slit experiment formula summary. And the second one you need to see is the angular position of the fringes. So a lot of students understand the Young double slit experiment, but where they falter is they are not able to memorize the formula. It is important that before you go for this examination, you must watch this YouTube video which I have prepared on the formulas. And also the second one I recommend for this question is the angular position of the fringes. Now let's start. I hope you will watch these two because it will help you solve this problem. Now I will definitely explain you the problem. Let's start studying this and work towards solving this problem. So this problem is a 5-marker problem, and let's read the question. Okay, the question is, the principle of superposition is used to understand the phenomena. So definitely, right, interference of light is based on principle of superposition. We use superposition to understand interference of light waves. Now the principle, which is a superposition principle, states that at a particular point, which is generally on the viewing screen, right? In the case of Young double slit experiment, there is a viewing screen on which fringes get formed. The resultant displacement produced by the number of waves is the vector sum of the displacement produced by each wave, right? So in a Young double slit experiment, you have two slits and the two waves come and they meet at the viewing screen where the energy gets distributed. And this is what they mean, the resultant displacement and the vector sum. It's a vector sum actually. It's not an algebraic sum like 2 plus 2 is equal to 4. That is not the way it works. Now, the light waves from the two coherent sources produce interference. It is important that in a Young double slit experiment, you always have coherent sources. You can watch my video on coherent sources. It is important to understand the necessary and mandatory conditions of Young double slit experiment. You can go to my YouTube playlist and find the coherent sources and all those things. All right. So Thomas Young was a scientist who did an experiment with two coherent sources using two identical pinholes, which are generally referred to as slits, right? And he used a single monochromatic pinhole source, right? And monochromatic light is also required because with the help of monochromatic light, the quality of interference pattern you get is very nice. You can use white light, but white light will not give you a very high quality of interference. It will give you a very poor quality of interference. Therefore, always use a single wavelength, which is monochromatic. All right. Using these sources in his experiment known as YDSC, the Young studied the interference pattern, correct? The pattern consisted of alternate bright and dark fringes. We already know that energy gets distributed. Wherever you have a constructive interference, you get a bright fringe. Wherever you have a destructive interference, what you get is a dark fringe. Now the distance between two successive bright or two dark fringes on the distance between S1 and S2, the distance of the screen from the plane and the wavelength of the light. So this is understood, right? So whenever the fringe gets formed, the distance between the successive dark and bright fringe depends on few factors. What are those factors? What is the distance between S1 and S2, right? This is factor number 1. The second factor is the distance of the screen from the plane of S1, S2, the viewing screen I was referring to. And we will draw a diagram. And third, of course, is when you use the coherent source, the wavelength of the light also matters. So whenever you study Young double slit experiment, you must be very clear that the gap between the bright fringe or the dark fringes, right? It depends on three things. One, the distance between slits. Second, the distance between the plane of the slits and the viewing screen. And third is the wavelength of the light. And therefore, I said, please ensure that you watch the formula video. Otherwise, you will not be able to solve this question easily. Go and watch that video so that your formulas are clear in your mind. Brush up your concepts before this exam happens of the board or entrance examination. All right. Now, first of all, let me just pick up the first one, and I will draw the diagram later. I think diagram should be known to you. That's the assumption. Let's talk about the question number one, and let's read it. Consider the following waves. Y1 is equal to A sine omega t. Second is Y2 is equal to sine omega t. Then it is 2 omega t, and then it is 4 omega t. Which pair of the waves coming from sources S1 and S2 will produce interference? Now, all right. So let's talk about coherent source to solve this problem, right? What is the concept of a coherent source, right? So what you do in a Young double-slit experiment typically is that you have a coherent source, and then you have two slits, right? Two slits. So this is your slit S1 and this is your slit S2. The single wave travels from here to here. Now, mind you, a coherent source, when it reaches the slit, diffraction happens at the slit, right? So you see this diffraction, which is spreading of the wave that happens, bending is happening of the wave, and then you have a viewing screen. Remember, in this particular question, if you see, for a coherent source, for these two derived sources, which is this one and this one at the slit, they're actually coming from a single source, which means the frequency of the wave, the frequency of the wave has to be same. You can't have two frequencies coming from the slits. Therefore, if you see this question, the frequency here is 2 omega, and the frequency here also is a 2 omega frequency, right? So coherent sources have same frequency, They cannot have a separate frequency, or they have same wavelength, one and the same thing. It is very important. They are actually a coherent source in Young double-slit experiment is derived from a single source. So here you have a single coherent source, and that gives rise to two separate sources. They appear to be two separate sources, but actually they're only one, because in the background they're coming from a single source. So the answer is 2 and 3, right? Let's see if there is a choice. 2 and 3. You can see this. What is this? This is the phase difference between the two. Phase difference between the two. Phase difference is allowed from the starting point, but what is not allowed is a different frequency. So wherever you find 2 omega t, right, the answer will be that. So second and third has 2 omega t because 2 omega is common in both of them. So answer B is the correct answer, right? I hope this made sense to you. Please understand that coherent sources must have same frequency, right? And the two waves which are traveling here are Y2 and Y3. So this is, for example, this is Y2 and this is, right, Y3. And they must have same frequency, which is 2 omega. All right, let's move forward to the next question. Now, the next question, and again, I urge you to please go and watch my videos on the topic of the formulas. All right, let's understand this. The second question is the light waves of same intensity I0 having a path difference of lambda by 4 emanating from two coherent sources meet at a point. The resultant intensity at the point will be. Now, see, finally in a Young double-slit experiment, what happens is energy redistribution, right? Energy redistribution happens, which means, the intensity is very high at the bright fringe. So you get very high intensity points, which are bright fringes, and you get dark fringes where there is no intensity at all. And you can see, so the sources which leave the slits, these two, for example, these two, as you can see, from the diagram, and I'll just enlarge this diagram so that you can see it easily, right? So these lights have the same intensity, right? So when they meet here, for example, the meeting point is here. Let's say the meeting point is this point, right? So the light which moves here, comes from this particular slit, travels, meets here, and then the light which is coming from the other slit also travels and meets here, right? So this is the way. So here you may get a bright fringe. Energy distribution happens. So individually this has I naught and this has I naught. But when they meet here, they meet, they do not meet algebraically, but they meet in a different manner, which is the as they have mentioned, the vector sum of the waves. So the energy which is getting created here, we need to decide what will be the resultant intensity. Okay, resultant intensity. And what is given in the question, that the path difference which is between these two waves is given to be how much? It is given to be lambda by 4. So let me just draw a perpendicular, right? And this is lambda. Okay, and the path difference which is existing, you can see this is the length, right? So this is the length which is traversed by, so for example, let me just label it so that you can understand it. So AB is the length traveled by wave number 1. The second wave is traveling another distance which is CB. So you can see, right, AB is one path which has been traveled, CB is another path, and the path difference between them is CE, which is drawn. So this extra, which is CB minus CA, right? You would have seen the words R1 and R2, right, is created, and this is another angle which is always given, delta, right? So CB minus CA is equal to the path difference. The path difference between these two in our question is given to be lambda by 4. Let's go back to the question. Now you understand the situation that due to this path difference, okay, due to this path difference, this is the path difference, which is this particular part, right, extra traveling. The path difference will create a particular type of resultant here. So the resultant intensity, the resultant intensity, the resultant intensity depends on the path difference, because path difference creates a phase difference. Go and see my video on the formulas and you will find a formula for resultant intensity. But anyway, I will write this straight away here. Let's go back to our question and read the question carefully again as to what is being asked. So what is being asked? They are saying what is the resultant intensity if the path difference of lambda by 4 exists. So the resultant intensity, I resultant, okay, I resultant is given by 4I naught multiplied by cos square phi by 2, where I naught is the individual intensity of the individual wave. So if you refer to the diagram, right, this diagram, you can see here the two waves that interfere, each has an intensity of I naught. It is meeting at this point and creating a resultant. So the resultant intensity we calculate is on the screen. Phi by 2 is the phase difference. So phi actually is the phase difference between these two waves, phase difference, right? So we know 2 pi is equivalent of lambda, 1 is equal to lambda upon 2 pi. In our question, it is reverse. We have given lambda by 4 as the path difference. So lambda is equal to 2 pi, 1 is equal to 2 pi by lambda, and lambda by 4 is equal to lambda by 4. So you can calculate the difference to be pi by 2. So our phi, which we have calculated using this conversion of path difference into phase difference, this is what we have done because we are interested in phi. So we have found the phi, and this comes out to be 4I naught into cos square phi by 2. right? So you have found your phi, which is pi by 2. So this will become pi by 2 divided by 2 is equal to 4 I naught multiplied by cos square pi by 4. 4 I naught. What is cos pi by 4 equal to? Cos pi by 4 is equal to 1 by root 2. So this is 1 by root 2 whole square is equal to 4 I naught multiplied by 1 by 2 is equal to 2 I naught. So let's go back to the choices which are given in the numerical and let's see which is the correct one, right? So let's go to this. Okay, so you can see the choice number C is the correct choice, right? This one, the choice number C is turning out to be the closest. I hope you were able to understand that this question was on resultant intensity. Okay, the maximum possible intensity in YDSC is 4I naught. If you have to find a general intensity, then it is proportional to cos square phi by 2, where phi is the phase difference, which may be given directly, or you will have to convert lambda into angle the way we did. All right, let's move forward to the next one. If you see the next one, there is a girl which has Vandana, who does the Young Devised experiment using different wavelengths, orange, green, red. If the fringe width measured in each case is this. So, this is a straightforward question. The only thing is, do you remember the formula of fringe width or not? If you know the formula of fringe width and you know that the wavelength of orange is big or the wavelength of red is big, you will be able to do that, right? So you should understand number one, what is a formula of fringe width? W width, right? In many books it is given as a beta, but I'm saying the width, fringe width, right? So W of a fringe is how much, right? And wavelength, how do you organize the wavelength of a red, green? Just by this basic knowledge, you will be able to solve this question. So let's solve this question and write all the values of the wavelengths, not the values, but the increasing order or a decreasing order. And the second thing we do is we write the formula of the fringe width, which you must remember. Again, go back to my video on the formulas or use your own book, memorize, put a paper where you can put all the formulas of Young double slit experiment in one place, memorize them up. All right, so the fringe width, okay, is given by lambda d by d, right? It is given in the question itself. If you read this question, you will find there is a formula for dependence of position of the fringe, and there is another formula which is different from what is given in the question of the fringe width. So lambda is what? Lambda is the wavelength of the monochromatic source. So this is the wavelength of the light which you're using. D is the distance between the screen and the slits, perpendicular distance. So if these are the two slits, this is distance where the fringe is getting formed. So this is your viewing screen and these are your two slits, right? So this distance is capital D and small d is the slit width, which is calculated, which is the distance between d, small d. If you understand lambda wavelength, you will find that the lambda of red is highest, right? Is highest. Then what is the other color given, right? It is, so you can write Vib Geor, right? So red is highest, then comes the less than, so great, this is greater than orange, lambda of orange. And then the orange is greater than the fringe width of green. I think the third color which is given is the green. So is greater than lambda green. Now, if you see, the experiment does not change, which means D remains same and the small d remains same throughout the experiment. So omega, which is a fringe width, is proportional to lambda here because d is not being changed, small d is not being changed. What you're changing is Vandana is performing this experiment with three wavelengths. So first wavelength she uses, for example, is WR red. She will get a fringe width which is red colored fringe and it is dependent on wavelength of the red light. So you can see it is directly proportional. The fringe width is proportional to lambda. So bigger the lambda, bigger is the fringe width. So you can clearly articulate, since lambda r is greater than lambda orange is greater than this, therefore omega r is greater than omega orange is greater than omega green. I hope this made sense. Now you're able to solve this problem easily, because first you have to memorize this formula. This is a formula for fringe width. Second thing, you have to know that the wavelength of red is the highest, then orange, and then green. Go and study about the wavelengths. Have a look at the values also, right? It will help you understand what is the type of wavelength a red wave carries. Let's move to the next one. Now, in the young, so which is a fourth one, right? Let's do the fourth one now. In a young double slit experiment, the slit separation is given. So, small d is known, and the interference is obtained on 50 centimeters. So, this is given to be 50 centimeters, right? Capital D is given to be 50 centimeter. And the first bright fringe is formed at 0.4 millimeter from the central maxima. So, the first bright fringe has been formed, right? Which is a maxima, by the way, right? Maxima, which means the intensity distribution, you remember. So constructive interference has happened at this place, and it has the distance at which it has got formed from the center. If this is your center, let me just enlarge this particular diagram so that you can understand, right? So this is the way you need to articulate, right? The center at which the both of them meet, right? This is the center, right? We call this as a central maxima, right? This is well understood. This actually is a zero order thing, this particular maxima. And if you look into the other maximas that get created, right, you must understand that uh, the one above this will be the first order maxima, the next one. And so on the upper side also the first order maxima is there, and on the lower side also there is a first order maxima, and between these two obviously there is a minima, which is first order minima. First order minima also gets created, minima. So first order maxima and minima, right? So you must understand, I'll just mark these separately so that you can watch clearly as to what am I doing. So with the help of this, so this is your first, so this is your central maxima, right? This is your central maxima. Let me just mark the first order maxima. So this is your first order maxima, and let's mark the first order minima. So these are the first order minima. So between the central maxima and the first order maxima, you have a first order minima. In our question, if you see, what they're saying is that the first bright fringe, right, which is the first order maxima, this is what I'm referring to. This is the first bright fringe which is getting created. Gets created at a distance of how much? Let's read it. I think it's 0.4 mm from the central maxima. So this distance is 0.4 mm. Let me just enlarge it for you so that you can see it very clearly. Okay, so this distance is how much? This is the distance being referred to. This is 0.4 mm. It is the distance between the central position of the central maxima. This is the position of the central maxima, and this is the position of the first maxima. And the distance between these two is 0.4 mm, right? So much information has been provided to you. What are you supposed to calculate? Let's calculate what is to be found out, right? So let's see what is to be found out. You need to find out what is the wavelength of the light which is being used. So what is the question? Find the wavelength. In terms of what? In terms of the position of the first order maxima. So you know your first order maxima, right, is where? The first order maxima is this place, right? So let's write the formula of the position of the first order maxima. If you know this formula, you can solve this in one sentence, and therefore I'm emphasizing a lot of confusion happens not because you don't know Young Double-Slit experiment, but because formulas are not clear in the minds of the student. All right, so I will just write down this cleanly. I have rubbed everything off. So the slit separation D is given to be 0.8 mm. All what you did was completely understand the question, may serve as a quick revision for you for your examination. Capital D is 50 centimeter, and the first bright fringe is formed at zero point 0.4 mm from the center. So this is used as Y is equal to 0.4 mm. And what are you supposed to find out? You're supposed to find out the lambda. And you're also given that n is equal to 1. N is equal to 1 because it is the first bright fringe which is getting created. It is not the central but the first one, first order. Now, if you remember the formula for fringe width, right? If I represent fringe width is given by WD by D, right? If you want to memorize the formula of the nth bright fringe, okay? The nth bright fringe, nth bright fringe. If you want to find the position of this, it's given by yn is equal to n lambda d by d. This is the formula, right? So in our case, we are given the position of first one. Y1 is given by n is 1, lambda is given by, we have to find the lambda into 50 divided by 0.8 mm. Now this is centimeter, right? This is centimeter, so I'll convert this into millimeters because everything else is millimeter, right? So this is millimeter, this is millimeter. I have converted this also into millimeter because otherwise my answer will be wrong. So small d is 0.8 and lambda is equal to, so y1 is how much? It is given to be 0.44. So I will change this to 0.44. 0.4, it's 0.4 into 0.8 divided by 500 is equal to 32 by 5 into 10 raised to power minus 4 is equal to 6.4 into 10 raised to power minus 4 millimeter. So I'm just leaving the answer in millimeter because I'm okay with this. And if you see the choices, this is one of the choices which is close to this, right? This is converted into nanometers. You can also convert this into nanometer, and although 6.4 matches with it, if you convert millimeter into nanometer, you can do that very simply. But since we've already understood it's 6.4, which is closest to 640, C is the correct answer for this, right? I hope this is clear in your mind that C is the correct answer. All right, let's move to the next one, which is the question on the angular separation of the fringe. So I'm doing the fifth one now, the last part. And mind you, I'm just doing it slowly so that you understand it. I can solve this in 2 sentences, but I'm going step by step. First I explain, then I solve. This is the unique thing about this channel, which you will find nowhere. So don't forget to subscribe because you're going to get some fantastic answers you will find nowhere. Consider the effect on the angular separation of the fringes in a Young double. So I hope you understand what is an angular separation. If you don't know, we will just discuss what is an angular separation for a quick revision. Although I expect that when you are doing these questions, you already have studied about angular separation. Go and watch my playlist on Young Double-Slit experiment and wave optics. These concepts have been beautifully explained in 1 line or 1 minute. All right. So they're saying, there is something called as angular separation of the fringes. And it says, what are the factors on which it depends? Okay. So he says, the question says, it depends on if the screen is moved away from the plane of the slit, which is, D. Does D impact angular separation? Then it says the separation of the 2 slits is increased till fringes are observed. Okay. So is it impacted by D? All right. So I have just, removed all the rough work. So let's understand that if you have a screen which is here, and then you have 2, and let me say this is the center. This is where the center the central maxima gets created here. And let's create, let's say you have the, one fringe which is getting created here, and then the second bright fringe is getting created here. So when you talk about angular separation of the fringe, what you mean is the angle which the fringe width, okay, a bright fringe, for example, this is the fringe width of a bright fringe, totally right. So this is a bright fringe which it is there. What is the angle which it subtends, right? So this angle, which is the angle subtended by the fringe, right, is called the angular separation of the fringe. So the angle subtended by the fringe is called the angular separation of the fringe. How do you calculate it? So this is d, right, and this is beta. All right, if I were to calculate the angle which it subtends, even though it is getting created somewhere here, we will see the midpoint here, right? This is the midpoint. So therefore the angle it subtends is this. Okay, had this been a single fringe width, the angle it will subtend here is the angular separation. So theta, which is the angle subtended by the fringe itself. So say this is your fringe. Okay, so this is your fringe. Okay, this is your fringe. This is the angle that gets subtended. And so how do you calculate it? Theta is given by the fringe width divided by the d, which is the screen distance, because this angle is subtended at the slits. Remember that, at the center point of the line joining the two slits. So if you have two slits like this, the angle is subtended here at the center. Okay, or if you're considering somewhere else, you can consider that position also. For example, I considered this position instead of just a center, right? Now the fringe, if you look into this formula, the fringe width is given by how much? It is given by lambda d by d multiplied by d. So d gets cancelled. So the angular fringe width or the angular separation of the fringe is given by lambda by d. Now look into the question. The question had dependency on capital D and on small d, right? You can see from this particular expression that capital D is gone, and what you're left with is that theta is equal to lambda divided by small d, which is the distance between the two slits. So if you consider the first one, the screen is moved away from the plane of the slit. No impact is there because the d does not appear. Capital D is not in this formula. Therefore, it remains constant is correct, right? But if you increase d, theta will go down, right? If you increase d, because these are inversely proportional, right? So the angular separation will decrease. So which means the angular separation is not impacted by the distance. D is meaningless because it got cancelled anyway. So theta is only directly proportional. You can change the angular separation by changing lambda. You can also change theta, the angular separation, okay, the angular separation by changing the slit distance. If you decrease the slit distance, the angular separation will go down, right? And vice versa. If you increase slit separation, the angular separation will go up. So it is reverse. If you increase it, this will decrease. If you decrease it, this will increase. Now, so far what we discussed was angular separation. One important point which I want to tell you, which is not part of the question, but they can ask you, is that finding the angular positions of the fringes. So one is a concept of angular separation, the other is a concept of angular position. So if you have this slit and this is your viewing screen, this is your, for example, the central point. If the fringe is getting formulated here, okay, the nth bright fringe, for example, is getting formatted here. This is the angle theta. Then the angle theta, right, how do you find this? This particular is given by n beta, if you remember, right? The total number of the nth bright fringe is getting created here at this position. This is y, okay, the y nth, right? So tan theta is equal to yn, the position of the nth bright fringe, divided by the distance between the screen, capital D. With the help of this, you can find this theta. This theta tells you the angular position of this fringe. So one is a word called as angular position and the second is called as angular position. Be very careful that you understand what is the angular separation versus angular position. Angular position is the angle subtended at the center by any fringe. So if this is the fringe, what is the angle it subtends at this particular point? This could be theta 1, right? But the width of this fringe subtends the constant angle which is given by lambda by d. The fringe angular separation everywhere is same, but each fringe is located at a different angular position which is given by this particular formula. So the position of the nth bright fringe divided by t will give you the angular position of the nth bright fringe. You can reduce y, the angle will change. You can also similarly find the angular position of dark fringes by using the position of the dark fringe as measured from the center of the screen, right? So for example, this is your yn minus 1, right? So from this point to the screen, this point, right? This particular distance. You can find this divided by d, you will get the angular position of the n minus 1th dark fringe. I hope the concept of angular position and angular separation also got clear in your mind. So this was a quick revision. Excellent question. You can also watch some of my videos where I've done numericals 1 markers for Young double slit experiment. You will learn a lot. I've done a video where I have 5 1 markers on my YouTube channel. It will be very useful if you can go through the whole playlist and do a quick revision of your board examination or upcoming entrance examination. So thank you very much for your time. You can see the difference. The channel is different because it gives you complete explanation and just not a single line solution. From solutions, you will learn nothing. From explanation, you will learn everything. And the concept will stay with you forever. If you listen to this video carefully, you will never forget what is inside a Young double slit experiment. Broadly, most of the points have been covered. Thanks a lot.